Hi, this is Physics Unit 1, October 2016. Let's go. Number 1. Which of the following SI units can only be used with a scalar quantity? So we have two kinds of quantities. One quantity is a scalar quantity and another quantity is a vector quantity. So a scalar quantity is a quantity in which we have only magnitude but we do not have any direction, and a vector quantity is a quantity in which we have both magnitude and direction. So scalar quantity only magnitude, no direction; vector quantity magnitude and direction. So what is a scalar quantity and vector quantity? So scalar quantity might be something that only has magnitude. So for example, time does not have any direction, right? We can have 1 seconds, 2 seconds, 5, 10, 15, 20, 25,000, 25,671 seconds or so. All of it do not have any direction, but it only has a magnitude. But in a vector quantity, it has a direction. For example, a scalar quantity can be speed 25 meter per second, but a vector quantity such as velocity can be a velocity is 25 meter per second speed with a direction of 45 degrees due east or due west, or 10 degrees due south, or 90 degrees due north, or something like that. So a vector quantity has a direction. So scalar quantity, part A, that can only be used with a scalar quantity. So meter is basically distance or displacement. So distance is the path covered, the total path covered. For example, we go from here to here and here to here, point A to B and B to C. We have 20 and 20. So the distance covered is 40, but the displacement is the shortest distance between these 2 points. So displacement is actually this with the direction of theta. So displacement is a vector quantity and distance is a scalar quantity, and both of them use meter. So A is not the answer. B is time. Time cannot have any vector quantity, so time is a scalar quantity. So the answer to this question is actually B, time, because time is the only unit that can be used with a scalar quantity. So C, meter per second. So meter per second, as I have told earlier, meter per second can be both scalar and vector. Scalar it is speed, and from vector it is velocity. So it is not correct. Part D is acceleration. Acceleration is always vector quantity, it is not a scalar quantity. So the correct answer is B. Number 2. A free body force diagram can be used to represent the forces acting on an object. So it is a free body force diagram. The diagram should only have forces, nothing else. Which of the following should not appear on the free body force diagram? From a block sliding down a slope. So basically the scenario is something like this. This is a slope, right? This is a slope and we have a box on top of it. So the forces acting on the box are, we have weight downwards, and we have the normal reaction force upwards, and we have friction in this direction Fr, and we have something in this direction which is, in this diagram it is saying acceleration, but it is a free body force diagram. This should not have any type of units except for forces. So this should not be acceleration of block. It should be the component of weight parallel to the direction of the ramp. So it is the component of force of weight. So this labeling should be component of force of weight, not acceleration of block. So this should not be the answer. So the correct answer to number 2 is D. Number 3. A load of 5 Newton is supported by two identical springs, each of spring constant 25 Newton per meter. Assuming that the limit of proportionality is not exceeded, the extension of spring is. So till the limit of proportionality is not extended or exceeded, we can use the formula F equals to kx, where F is the force, x is the extension, and k is the spring constant. So we have a spring constant of 25 Newton per meter, but as we can see in the diagram, there are two springs. So using two springs, so the total spring constant of those two springs added up is 50 Newton per meter. So the value of K is 50 Newton per meter, and the force is the same, 5 Newton. So 5 Newton is being exerted, the force is being exerted on a spring of 50 Newton per meter spring constant, and we need to find the extension del x. So del x would be 5 by 50. So the answer comes as 0.1 meter. So the answer to question 3 is A. Number 4, the diagram is taken from a multi-flash photograph. So multi-flash photograph is basically we click several photos of the same scenery, keeping the camera at the same position. So of an object falling in a vertical plane. So it says that, for example, the scenario can be described as, for example, we have a plane here, the plane is going in this direction, and someone just drops any object from the plane, and this is the ground, for example. So the object will be traveling like this, and it will fall to the ground eventually, right? So this is what, so the story of multi-flash camera is, from the moment the object is released from the aeroplane, when the object is here, one photo is clicked, another photo is clicked after 2 seconds, another photo, another photo, another photo, and till it reaches the ground. So this is the type of scenario that we are dealing in this question. Select the row of the table that correctly describes the horizontal velocity and the vertical velocity of the object. So the horizontal velocity and the vertical velocity, let's see here. This is the horizontal and this is the vertical, right? This is the vertical. So we need to see the horizontal displacements and vertical displacements with time. So let's see the horizontal displacement. For the first second, the horizontal displacement is this length. For the second, it's this length. For the third second, it's this length, right? So we can clearly see that the distances are actually decreasing. So since the distance covered per unit time is decreasing, we can also say that the velocity is decreasing, the horizontal velocity is decreasing. So the horizontal velocity is decreasing. So either option A or B would be the answer. Let's see the vertical displacements now for each second. So the vertical displacement is this for the first second, second second, third second, fourth second, 5 second, and 6th second. So for this scenario we can clearly see that the displacements are clearly increasing, the distance between them are increasing with time. So this means that distance by time is actually speed or velocity. So the vertical speed or velocity is increasing. So this or this. So the correct answer is actually A, since only in A both of the columns match. So the answer to question 4 is A. Question 5. A force F is applied to a box, causing the box move along a horizontal surface. Which of the following would produce the most work done by F on the box for a given horizontal displacement? So most work done is basically work done is equals to force into distance, right? So greater the work done, greater the distance, right? Most work done for a given horizontal displacement. So basically the horizontal displacement would be constant. For higher work done, there should be higher force and a constant distance. So higher force, we have four scenarios: part A, B, C and D. Part A says that it's 45 degrees upwards, 60 degrees upwards, 30 degrees downwards, and 45 degrees upwards. So for part A, basically the horizontal component of force is F cos 45. For this it's F cos 60, and the other would be the same as follows: F cos 30 and f cos 45, right? So let us see how does the value of this cos 30, how does the value of 30, this value 30 cause a change in the value of cos 30. So when the value of theta or 30 increases, let's see what happens. Let us just draw a graph of theta against cos theta. So we have the value of theta. When the value of theta is 90, cos theta is 0. So 90, 180, 270 and 360. So we can clearly see that from 0 to 90, when the value of theta is increasing, the value of cos theta is decreasing. So lower the value of theta, higher the value of cos theta. So what is the lowest value from these diagrams? 45, 60, 45, 30. So 30 has the lowest value. Since it has the lowest value, it will cause the highest value of cos theta, thus the highest value of force. Since it would have the highest value of force, it would give the highest value for work done. So the answer to number 5 is C. Number 6. The following extension graph for a wire is shown. When a force F1 is applied across the end of the wire, an extension E1 is produced. So which of the following correctly describes the work done to extend the wire? So basically the work done is basically the area under the graph, right? So it is the area under the graph. So the area under the graph is this basically. So area under the graph is this shaded area. So this shaded area is the area under the graph, right? But the 0.5 half E1 F1 is basically this. So if this is the half E1 F1, it says that the work done is actually greater than the 0.5 F1 E1, right? Usually what we do is we take the readings till the limit of proportionality. Since this is a triangle, so half 0.5 F1 E1 is actually equal to the work done, but after it exceeds the limit of proportionality, it is not directly proportional now, and so in this case the work done is actually greater than the half F1 E1, right? Half F1 E1 is basically this, and work done, the total work done is basically the area under the curve, the total area. So this area under the curve, the whole thing. So the work done is basically greater than 0.5 F1E1, so the answer is B. Number 7. It can be deduced from the graph that up to force F1 the material is. So you can see in the graph that after F1 the wire breaks, right? Since there are no curve continuation, it means that the wire has broken, but up to F1 the wire was there, it did not break. So up to F1, since it did not break, it is strong or tough. So tough is the answer. It is not brittle, because if it was brittle, it would have, the graph would have ended somewhere before, like this. The graph would have ended before F1. So brittle is not the answer. Elastic is not the answer, since up to F1 it is not elastic, since for example at this point, if we remove the force at this point, it would go back to its original position. At this point it also would go back to its original position, but somewhere here is the elastic limit. After applying this force, for example F2, it would not elastic, it would not return to its original position. So it is not the true case that up to F1 it is elastic. If we remove the force F1, it would not return to its original position, and malleable is also not correct. So the correct option is D. Number 8. A child throws a ball vertically upwards and catches it while it falls back down. So a child just throws a ball into the air, and it goes to the topmost position and it goes down again, and then he catches the ball. So when the ball is caught, the ball exerts a force on the child's hand. So for example, this is the child's hand or any surface, or and this is the ball, right? So upon impact, when it is in impact, when the ball is in impact, ball has a motion downwards, right? The ball has a motion downwards, so it exerts a downward force on the surface. So Newton's third law states that every action has equal and opposite reaction, and the other clear way to find Newton's third law is that when object A exerts a force on object B, then object B exerts an equal and opposite force, equal in magnitude, and opposite force on object A. So for example, object A might be the ball and object B might be the hand, right? So since when the object A or ball exerts a force on the child's hand would exert an equal and opposite force on ball, right? So equal and opposite, it says that the ball exerts a force on the child's hand, so the force from the ball is downwards, so the equal and opposite force would be upwards, right? So either C or D. And then the ball exerts a force on the child's hand, so a force is exerted by the ball on the child's hand, so an equal and opposite force would be exerted by the child's hand on the ball, right? By the child's hand on the ball, so of the hand on the ball. So the option is D, the correct option. Number 9, an object of radius r and mass m falls through air of viscosity n. At terminal velocity mg is equals to 6 pi nrv. So basically at terminal velocity there is constant velocity. Terminal velocity is known as the constant velocity. So at constant velocity, it means that the velocity is not changing with time. If the velocity is not changing with time, the acceleration is zero, right? Since the acceleration is basically the change in velocity by time. So since it is not changing, the velocity is not changing. If the velocity is not changing and acceleration is zero with a constant mass, there will be zero force. There won't be any resultant force. So since there aren't a resultant force, if we draw a free body force diagram, the body will experience weight downwards and drag upwards, right? Drag upwards of 6 pi nrv. So in this case we can prove that mg equals to 6 pi nrv under terminal velocity. Then there are some assumptions that the sphere has to be small, and if the sphere is small, the flow across the sphere is laminar, right? It's a laminar flow if the sphere is small, and if we want to apply the equation mg equals to 6 pi nrv, so it should be laminar, right? So if the ball is bigger in size like this, if the radius of the ball is bigger, then there shouldn't be only laminar flow. Like there might be laminar flow like this, but there should be turbulent flow across the surface of the ball. So the radius of the ball should always be small, so that laminar flow can exist. This is the laminar flow and this is the laminar flow, but these are the turbulent flows, which we do not want if we want to apply this equation. So which of the assumption is not correct? The airflow across the object is laminar. This should be correct, as I have told. The object is a small sphere. This should also be correct. The speed of the object is very high. This is not correct, because if object is a feather, it is not necessarily that the feather will have a high speed, right? So C is not the correct assumption. Is the correct assumption since it falls through the air. The upthrust is basically the upward force exerted when the object is traveling down any fluid, any very high viscous fluid. So is also not correct. It was in water. So D is correct because it is in the air. So C is the answer for number 9. Number 10. So before I start number 10, if this video helped you this far, please consider liking and subscribing. This motivates me to make more videos and help you guys. These videos take time to make and really have to put in a lot of time and effort, so a like would be appreciated. Should be appreciated. So number 10, computer printers form an image by placing a series of correctly placed microscopic dots onto a paper. So these are the dots that are placed onto the paper. If the temperature of the ink is too high, the size of the dot will increase, producing darker image. So a higher temperature would produce a darker image, which shows that the flow rate is high with a higher temperature, right? The flow rate is high in this and the flow rate is lower in this, since more ink is flowing with a higher temperature. Select the row of the table that correctly describes the effect of increase in temperature on the viscosity and rate of flow of ink. So we have a graph of viscosity against temperature. You guys need to memorize it. Temperature and viscosity. So temperature and viscosity are basically inversely proportional. So when the temperature increases like this, when the temperature increases, the viscosity actually decreases. So with an increase in temperature, there is a decrease in viscosity. So decrease in viscosity, and viscosity is basically the resistance to flow, right? The resistance to flow is viscosity. So since the viscosity is decreasing, the resistance to flow is also decreasing, so the flow rate would increase, right? So the flow rate would increase. So the correct answer is C. Hope the video helped you guys. Thank you for watching.